So it's wonderful to have Armelle Kloppenburg here with us today. Armelle is a Dutch structural consulting geologist. She constructs digital structural models on all scales. So with her experience, it's going to be amazing to hear about 2D, 3D and 4D structural modeling to minimize uncertainty and risk in geological interpretation, or how to meaningfully collect the dots with limited data. Thank you so much, Armelle.
Jess, well, first of all, thanks. I'm really honored to be a part of to contribute to part of your to contribute to your series of very impressive talks, and I'll be talking about the use of structural geology to minimize uncertainty and risk in the geological interpretation. It's I should say a talk that it's a slightly longer version of a talk that I've given at the SCG annual meeting last September, and it is not going to be a highly technical talk in terms of structural geology, but it really aims to, I suppose, inspire people to show what can be done and to inspire them to use structural geology a bit more. So I've selected a number of aspects that I think are most useful, and there we go. I've been allowed to show some case studies. I'm very, very grateful for that. So that's the acknowledgement there. But first of all, what is structural geological modeling? It's first of all a description of the current geometry of the geology in either in maps, sections, ultimately in three-dimensional models, but it's also about understanding the geological history that's behind it, and so it's about a good story to go with the model. It aims to produce an internally consistent and a valid, at least allowable interpretation, and on top of that, it is in my eyes, also a quantification of not just the geometry as it is today, but also how that came to evolve through geological time. So time is the fourth dimension. So I'm just going to take a sip. So the time being the fourth dimension. As we all know, all models are wrong. Some are useful, and a structural geological model is useful when it allows you to ask and answer the key questions, and that could be different for different teams, whether you're in greenfield or brownfield exploration, or in more local, the ore body scale, or whether you are in engineering, worried with the stability or of the mine design. So a geological model can be at different scales, different level of details, and may have different structural parameters, from kilometer scale faults to highly detailed fractures. If only I had the whole day, I could take you through a range of them, but I've selected a few. So I'll take you through why structural interpretation is important, because the structures form the plumbing system for your mineral system. I'll then explain it's important to have a good three-dimensional description of the geometry, both before, during, and after mineralization. I'll give you a flavor of what I think are the most useful tools and techniques to address the uncertainty in structural interpretation. So none of this is rocket science, really, but in my view, I think many of these are underused. I'll show you how kinematic modeling is used to test an interpretation and improve the understanding of the geological evolution and how it came to be. And in the end, or at the end, I'll show you how seismic, in particular 3D seismic datasets, can help to minimize that, uncertainty and help constrain the interpretation. First, a bit on mineral systems. When I started working as a structural geologist with Anne and Gibbs and his consulting team in Scotland some 20 years ago, now. It was initially on petroleum projects, and the concept of petroleum systems was coined by that time by Magoon and Dow, and it was well established. And a petroleum system involves a flow of hydrocarbons, typically from a lower source up diffusely or along focused flow routes to a trap here formed by a local dome. And there was a central role for time. And it was really important to have all the components of that system in place, in the right order, in the right relative order, for that system to be successful. Okay, so everything needed to be in place in the right time. And the geometry of the geological components in this particular case, stratigraphic layer, or it could be a fault, or were crucial to define where that exploration target could be, because they were crucial in defining the geometry of the fluid migration pathways. And any deformation, any change of shape had a direct consequence, you can imagine, for the system and for the location of the exploration targets. Now, at the time, we said, okay, well, consider, rather than oil and gas, petroleum fluids, consider fluids that are gold bearing, for example. Same philosophy applies. Slightly more complex, and it's of course not the fluids that get trapped; they get focused, but it's the minerals that get trapped. So, of course, mineral systems, as understood and used now, is much more complex, much larger, and it's been really studied and published on and well defined by people like Ken McQuaig, John Wronski. Fluid flow at crustal scale is obviously still a hot topic today. This diagram is from Cam and John's work there. Central in this system that works at different crustal scales is the structural architecture. The structural architecture plays a central role. Okay. That structural architecture is formed by a range of different structural objects, faults, fractured volumes, permeable stratigraphic beds, shear zones, and at the largest scale, translitters with fault zones here, really beautifully imaged in a system for porphyry copper by the diagram Jeremy Richards. And collectively, so they form that interconnected plumbing system. So in your structural modeling at any scale, first of all, you want to aim to define the geometry and the connectivity, or the interconnectedness of all those different objects in 3 dimensions. First of all, their present day shape, but also the evolution of their shape and their connectedness through time, particularly, of course, at the time of mineralization. First things first, though, a good 3D structural geological interpretation. We all know geological models are inherently under constraint, and many geological interpretations are made. Maps, sections, 3-dimensional models, beautifully looking 3-dimensional models, shiny models, but how do you know an interpretation is right? Because we all know if you connect 4 drill, or if you ask to connect these 4 drill holes up, you may get many different scenarios. So if your geological model is uncertain, then any prediction based on it is high risk. And just to illustrate the difference between uncertainty and risk, I found this image usually works quite well. I think you can all feel the risk here. Of course, the uncertainty lies in the behavior of the horse and the skills of its rider. But the rider can be trained, the horse to a certain extent. In exploration and mining, the uncertainty of structural geological model can be addressed number of ways. So I'll take you through that. The uncertainty in geological in structural interpretation can be minimized in two ways. On the one hand, by taking into account prior knowledge, things like geological context, geodynamic setting, the tectonic, tectonostratigraphic context in which the mineral system may evolve. And on the other hand, by aiming for geological sense. And I've selected 4 topics that I felt would be most useful and interesting and make the most difference. So this talk is really about the latter. Okay. It's very much focused on hands-on structural modeling. Constructing maps and sections. First of all, and this will not, it'll be for research, people in research and for medium, larger companies, it goes without saying, digitize and georeference any old data sets, paper maps that lie in the corner of your office, maps and sections, and integrate all data in 3-dimensional digital georeferenced space, which allows you then to compare and contrast things at the same scale. You will remember having air photographs and plastic overlays, and then what do you call them, sterile overlays, and then your geological map at a different scale and your satellite imagery. So all of that, get them in the same space, really. And as I said here, when joining the dots on drill holes, and now I mean literally, when you are working with drill hole data, make sure when you log your data, your drill holes, make sure that you collect data on the orientation of your stratigraphic beds, on your veins, on your structures, and use those to constrain, whether your target volume is horizontally oriented or collection of steep structures there. Okay, trivial and obvious things, but I could see it happen in many projects. This just doesn't happen because of lack of time or lack of insight, I suppose, and how you could use. Point number 3, use stratigraphic thicknesses to help you understand the evolution of faults. And Titus, in his talk earlier in this series, mentioned how thickness changes can relate to either extensional or contractional faults. So you still need to put that in context, but it all helps. Stratigraphic thickness variation. And then last but not least, when you record and interpret a fault offset, be aware of the complexity, possibly due to reactivation of maybe some earlier initially extensional fault that gets, that hanging wall gets pushed back up during subsequent deformation phases that are contractional. So the current offset may not tell you the whole story, but look for that story, I suppose, is the central message. Point number 2, testing for validity. So testing whether your interpretation is possible, makes sense, is consistent. Okay. What you need to do for that is you need to integrate your data into 3D modeling space, and that includes geological geophysical maps, your cross sections, your long sections, your drill hole data, also the ones that you didn't use yet for constructing those sections, and your pit or your underground mapping. And then a warning is that when you put everything together and you connect the dots, that model is not always constrained, and therefore your connection is not always right. So you still need to test your interpretation for validity. Okay. And even when your sections are correct, a series of cross sections need not always lead to a correct 3D model if you connect those interpretations up. And I'll explain that a bit more. And this is an oblique view of a three-dimensional model, an example. It's built based on a series of 3 seismic cross sections through the highlands in Papua New Guinea. So that those cross sections are not trivial. They're long, 10 to 15, 20 kilometers long. Interpreting the seismic is not trivial to start with, but to connect the interpretations up into a 3-dimensional model is high risk, because only if you compare these the seismic sections and integrate them with the geological map, you'll see that the structures are highly non-cylindrical, meaning that they're not the same. You can't connect one fault to the other in your cross section. And there's a long story there, but it has to do with the inherited extensional faults in the Triassic and older rocks, and the angle between these extensional faults and the subsequent inversion direction, so the direction of shortening, that caused inversion of these extensional faults and the locally thick-skinned, but also locally thin-skinned thrusts above. And you can see here there's a whole set of them at a high angle to the overall trend of the structure. And you have some transfer, some accommodating faults that are nearly vertical here in rainbow colors. So you need to zoom out when you interpret these things. You need to know about you need to get your head around the regional geology and any constraints that you can get, basically integrate sections with maps. But you can imagine that, well, it's easy to see that if you don't have the outcrop, or if you don't have the constraints from the surface, then working with sections alone is high risk. And if you think about it, there's many areas where there simply is not a lot of topography. There's not a lot of surface outcrop. So, and the sections are all you can work with, and some drill holes if you're lucky. So, so that's that. Testing for validity, number 2. It's about the use of kinematic modeling, so integrating the time aspect of geology to test whether an interpretation is possible to start, whether it's valid or feasible or likely. Kinematic modeling builds on 2 principles. The first one is that the real world always balances, so there are no unexplained gains or losses of material. Okay. Of course, there's lots of geological reasons why things may disappear, by erosion, for example, but that can be addressed, can be explained, expected. The second principle is that the geometry of an underlying fault, and here you're looking at a sandbox by Ken McClay, that's an extensional fault, it's a listric extensional fault, so it's not planar, but it's got some shape to it. And because of that listric shape, the rocks that are being pulled down need to change shape as well. And there's a relationship between the 3 things. It's the amount of displacement, the shape of the fault, and the way that the hanging wall, in this case, changes shape as well. And nervous here, and you can see that the hanging wall has changed shape by a series of second orders, so smaller but closely related to that first order fault. A series of second order faults. So some are dipping the same way, the synthetic faults, and others are dipping the other way, and collectively they kind of allow the rocks to change shape. These principles are the basis for a series of computer deformation algorithms, and there's software that uses these algorithms to mimic how these rocks deform, and they work in 2 dimensions and 3 dimensions. So it's a bit of crossover technology. I think it's been around for over 20 years in the oil industry originally, and it's made it over to the mining industry. So I'll give you an example here where, and this is in the Swiss Alps, Jura, the northern Switzerland. It's a fold and thrust belt, and you can see constraints from the surface here. We're here in the northwest towards Germany, that's the southeast. There's a data from a whole outcrop. There's data also from 2 tunnels that you can see. If you've got good eyes, you can see here running through the mountains. The aim of this exercise was to predict structures with depth, and that has to do with the geomechanical laboratory that sits here, the Monterey laboratory that sits here along that tunnel. So data from, if I flip back and forth, the data from the surface and the tunnel have been used, and the systematics have been used to predict structures with depth. And this is really the result of a series of iterations where interpretations are restored, tested for line length balance. Does everything fit back together again? Can we forward model it and fine tune it? And there's about 12 time steps now I'll show you in that process. It's important to realize that the base for this stratigraphic sequence is formed by a series of weak salt-rich stratigraphic units that act as a natural detachment. So that's a relatively weak zone there. So it's a horizontal detachment parallel to stratigraphic units. But there's an internal stratigraphic layer of shale that has acted as a detachment as well. So it's important, I would argue, to really look at the mechanical properties and the relative strength of your stratigraphic sequence to pick them and to argue their effect on the structural geometry, on the geometry of faults, on how deep these faults go. And then there's a relationship with older structures, inherited structures with the basement, but I won't go into that. It's another tool. So 12 steps to show, first of all, that's the eroded rocks restored or reconstructed, I should say. And then there's a series of thrusts that I'm going to take the reverse displacement off. Starting here in the southeast, it's the anticline there. There's a 2-step rocket for it. Then the next step is going to restore that wedging, that thrust here, and that has, as the thrust kind of developed, it never made it up to the surface because it got stuck, if you like, and then it connected up to a parallel shear, parallel to that weak opalinous clay zone. Okay, so that's that wedge gone. You can see how the emplacement of that wedge has caused that bump, that initial bump to start with. And then it's the frontal thrust restored in steps, the Monterey thrust it's called. So there you go. Now a structural geologist would say, oh, that balances nicely. There's no overlap, there's no gaps to be filled, or so that balances nicely. So the rocks before deformation are all accounted for after deformation, if you like. Of course, we've included some of the reconstruction of the eroded rocks. It's fine. Okay. Now, this is just one scenario of a whole series of possible solutions to getting to that present-day geometry. The interpretation of that in this particular scenario. Now, not far from where we were working here, there was a different group that proposed a different structural solution. It leads to the same geometry, if you like. So it's consistent with the surface structural geology as we see it, but it has a severe duplication of some of the older rocks here in this area. We prefer the scenario, the first scenario, for a number of reasons, for mechanical reasons, but also at this scale, at least, the line length balancing it's not working for us. So you've got a shortage of the blue and green units at the top. Now they may be pushed all the way to the north, but at this scale, the model that we're looking at here, that balance doesn't work. The Jura mountains in Switzerland are not as simple as this section suggests. Again, if you integrate it and if you look at it with the geological map, you'll see that there are folded There are big folds that plunge away, and then there are thrusts, they stop, and other thrusts pick up. And I tried to image that here in my paper model of a compression or contractional relay ramp, really, where you have this thrust here that tips out, the other thrust there that tips out, and where they overlap, you have an accommodation zone, contractional relay ramp with the tectonic transport towards the bottom left. So you can imagine if you take a section through here, and if you take a section through the middle, then they're going to be very difficult to, if you only have those sections, to build a three-dimensional model of, because they simply are too different. It's one of the tasks that the Geological Survey of Switzerland, Swiss Topo, are working on at the moment, making a three-dimensional model of the Jura in Switzerland. It's a challenge. In testing for validity, there's software to help you. Of course, you could do this by a piece of string and paper and pencil, but it helps to have a piece of software to help you with this. And the algorithms that I've mentioned before will help you to restore any effect of folding, of faulting, whether it's extension or contraction, erosion, sedimentation, but also, you know, on big regional lines, things like area isostasy, flexural isostasy. So that's it's a really good tool it's a useful tool to have. And then last, number 4, last in this series, 4 things, is comparing your interpretation to concepts for structural style. And that's you could talk a week about that. But, to identify an appropriate structural style for a particular area is people divide structural regimes into extensional regimes, contractional regimes. That's a Crestel scale. So, for example, identify thrust, faulting, or inversion to be an important way in which rocks deform. It could be strike slip regime or deformation related to salt and movement of mud, so mud tectonics. This is all driven, of course, can be driven by prior knowledge, knowing where you are, in what kind of tectonic setting you are, and the geological history. So this will give you a ballpark, if you like, a start for the interpretation and for the structural style. And it will give you potential alternatives to test. Significant in this is as I said, the mechanical stratigraphy. It's crucial for your structural interpretation. And often you have to make assumptions on that, so you have to play or may entertain different scenarios on that topic. I'd recommend to consider first and second order structures as we looked at that extensional fault. It's important to know when you're looking at structures which ones they are. Are they the main structures, or are they just the second order, maybe even third order structure? So make sure that you think or consider that. Okay, and then there's of course a whole topic on the structure assisted emplacement of intrusion, which is a bit of a talk by itself, but fundamental to get that structural style right, particularly on the topic. So even if you know or think you know which regime you are in, and I'm just going to take one of the most straightforward, an extensional regime, there's still lots of uncertainty and lots of different styles that you may want to test or consider. So I've visualized 2 end member structural styles, if you like, for extension here. There's a domino style extensional faulting that has straight faults and fault blocks that are internally not that deformed. On the other hand, already talked about briefly, the Listric style extensional faulting, where you have a significant shape change of the fault blocks. Here, in this case, the hanging wall as a whole. But depending on the scale, that you look at. There's a bit of terminology for that. I'll put that down. Further uncertainty or complexity is caused by the fact that these extensional faults, and here you're looking at a three-dimensional model, are often not laterally continuous, like in the Swiss Alps. Extensional faults may tip out, may stop here, and then another extensional fault may take over, and you have these complex relay, what they call relay ramps, so that where the stratigraphy is actually continuous there. Often in these areas, some of the deformation of the rock still needs to be accommodated, but not by one big fault, but more likely by a series of smaller faults, highly fractured. It makes it a bit of a target by itself. I should say, the location of these relay ramps is often dictated by complexity that sits underneath, by inherited larger scale faults in the basement, inherited basement faults. And here's an example where from southwestern Mongolia, it's the Bayanhundi epithermal gold deposits that on the bottom left here, you're looking at a map, and you can see in color-coded for depth a whole series of zones that have high gold values. And you can see that these zones are relatively short, but that collectively they form their envelope, if you like, forms a rather long zone. It was a bit of a challenge to explain their overall geometry and their existence. Long story short, one of the current preferred structural scenarios is that these have formed in an extensional relay ramp, where these individual zones are sort of the second order fractured zones that are, of course, the location where fluids may focus or may be allowed to travel through, you know, as they come up the extensional faults into the rocks favorable for mineralization. Longer story. Having this concept, whether it's right or at the moment it still lives. I should have said at the moment of interpretation, the drill hole constraints were not there to test deeper, but the drill hole constraints are there now, and these extensional faults may potentially be the targets for a bigger prize. Okay. If only we could have additional data to bring us to structural interpretations, the structural style, easier or quicker or sooner. And I'd like to highlight the use of seismic, and especially the high resolution seismic acquisition and processing that is carefully designed for hard rock terrains. If you're after deposit scale structures in their larger context, then 2D seismic lines, or even better, 3D seismic cubes have proven really useful. Okay, and I'll give you an example of that. Of course, if you're chasing large translithospheric structures, then you need to resort to deeper, longer 2D crustal scale lines, and these are often driven by research. They're often government funding. There are many wonderful Australian examples, and but here I've chosen to show you an example across a modern subduction zone in southern South America. So this is a line that was it's a big regional seismic line. It's about 370 kilometers long. It goes about 100 kilometers deep. It was published by the NCOR group led by Onno Onken some 20 years ago already. and it is spectacular in Onderwonken and is a large intermission thing. It's impressive what it shows. Their interpretation, you can see here's the subducting oceanic slab going down. It's the oceanic crust that I'll flip back and forth that shows up on the seismic there. You can see these highly reflective packages interpreted to be caused by melt-rich layers. That's the present-day volcanic front sitting there, potentially linked. It's spectacular what it images. But of course, this seismic at that scale won't point you to the location of ore directly, but it will give you context for to more local data sets. It may help you define, of course, this is the scale that may help you define the nature and the location of some of the deeper seated translithospheric structures. Okay. Now zooming in, an example closer to home. This is a three-dimensional seismic cube from the Karasu Dam gold project in the Archaean granite-greenstone belt in the eastern goldfields in Western Australia. And here you're looking at a horizontal slice through it. So it's a 6 by 8 kilometer footprint, and that's a kilometer grid behind it. And you're looking at a slice that sits at about 700 meters below sea level. In yellow stars here are the known deposits projected to that level. And to me, it's impressive that you can see on this depth slice alone a wealth of information on trends, continuities, discontinuities, and cross-cutting relationships. Okay. And the seismic reflectors are interpreted to represent contact between rock types with different acoustic impedance. Impedance being, and I'm sure that if you've joined the talk this morning, which I'm afraid I had to miss by the company HiSeis, they will have told you in much more detail that the impedance is needed to give you these reflectors, and it's the product of the density and the seismic velocity of the various rock units. And it's only the contrast in impedance that gives you that reflector, and the strength of that reflector is the amplitude of the seismic, if you like. It's the result of the amount of contrast between that. Now that contrast is not only caused by the difference in rock type, but also by alteration. It may, and by deformation zones, deformation structures, or leave it at that. And whereas structures and fault planes that are quite steep are not expected to form good reflectors because of their steepness, even though some faults actually do, they can be recognized by the breaks in the reflectors that we do see. Flip back and forth. It takes a little while to tune your eye into that. There's a wealth of information. So I'll take you down through a series of depth slices here, and even though the resolution, you lose the resolution as you go deeper, quite deep actually. You can see the continuity. You can also see a step in where these reflectors are with depth, which will give you the, it's a reflection of the dip, of course, of the lithological units and the structures. Going down further, some 2 kilometers, you see below sea level already. So with the help of a series of depth slices, you can map out the most significant structures in 3 dimensions. So it's particularly useful when you have no outcrop or no surface geological map. Okay, going down, now you're losing resolution. Here you have some long sections, some cross sections, and if you I'll take you through various visualizations or combinations of that. That's the pit sitting there. So you have some of the first order thrusts sitting interpreted where they where they are, and they connect to surface where we know where they are. You can see that these thrusts don't continue laterally. They kind of ramp up to form side walls. Little splays come off them. There are some structures at high angle that you can map out. There are some structures okay, I'll leave that. And then based on a series of slides like this, and a series of sections and cross sections, you can start to map out these faults and these structures, or the key ones at least, in 3 dimensions. And then you can start to analyze where cross-cutting relationships exist and where you have a spatial correlation with known deposits. And with that information, you can look for additional targets. So this work is work in progress. It's the result of 6 weeks of work. But what you do, you identify the main structural components and work from there. All right, that was it. Longer than I was planning to do. I hope I've inspired you all a bit by highlighting what I think are the most useful tools and techniques for structural interpretation at various scales and with various reasons. Thank you. Again, acknowledgements for the people that have allowed me to use to show company data and project results.
Thank you so much, Armelle. That was that was a wonderful talk. So thank you.